Chapter 7. I think I mentioned earlier in the semester that the periodic table is chock full of information if you know how to read it. And we're going to spend this chapter learning much of what's contained in the periodic table. It assumes this current form because of the way atoms are built, the way atoms are structured, lends itself best to this arrangement of elements in the periodic table. You can find various versions of the periodic table. Some people trying to make them more useful, and some people just want to add to the confusion. One periodic table that I would love to have is a physical, like a board game. It's about that big. And each one of the elements has a sample of the element glued to the little square, except for some of these down here because they're radioactive and you can't get them anyway. But I'd love to have one of those. But it's arranged the same way as this one. So we're going to start off trying to learn what we can about the structure of the atom. And we know some things about it, but I want to hammer some interesting points. One is that most of what we know about the universe comes to us by way of light, if we know how to read it. And that was part of the learning process as the modern scientific age began, is why are things colored differently? We could see different colors, and eventually we moved out from the colored area into regions that we can't detect. One of the first was infrared. I'm trying to remember the name of the scientist whose experiment didn't involve, it might have been Isaac Newton, didn't involve the colored area. He thought if he moved his thermometer out of this splitting of light into its colors, if he moved his thermometer away from them, and he happened to move it away from the red, the temperature went up. Whoa, wait a minute. I don't see any light there. In fact, there was light there, the infrared. Anyway, fireworks are a good example of different colors. Some of the fireworks, they're easy to make those colors, like the oranges and the yellows. I mean, there are several elements that you can put into your burst that will make those colors. White's not too far off. The ones that are really hard to make are the blues and the greens, but they can be done. So the natural question then that arises is, why do we get these colors? You know, why do different chemicals give different colors? One of the demonstrations I used to do when I worked in research is I had this device called an atomic absorption spectrophotometer, and it had a flame in the middle of the instrument that was fed by acetylene and compressed air. Or we could switch over to nitrous oxide instead of air. And that was for just particular types of elements. Come join. And this device would suck up samples. It would aspirate samples into the flame, and it would atomize the sample into its individual elements. And we would adjust the height of the flame so that we could look through the flame where the neutral atoms were located. And then we would shine light of a different certain wavelength through there, and it would be one that was characteristic of one element or the other. And we could measure the amount of energy going in, the amount coming out. We could quantify the concentration of the element in our sample. But depending on which element I aspirated into the flame, it would give me these different colors. So when we had, especially grade school and early, like junior high would come through, I'd hit them with all different kinds of colors. Seems like their favorite over the years was strontium, because it would give it a hot pink. And understanding how these colors are produced gives us information about which elements are there. Why does a chemical yield different colors when it's treated differently? Like in the flame, it might be one color, but when you put it in solution, you get a different color. So it has to do with the way water associates with the element. Why are some colors common to different chemicals? Some chemicals have very similar colors, like this one. The zinc and the calcium are close, right? Zinc is more yellow than calcium is, but sodium, it depends on the temperature too. If you get the temperature, if you raise the temperature for sodium, it's going to lean more toward the orange and the yellow. Examples: oxygenated blood. Right? If you get blood from, if you have blood gases done, they got to go deep. Get your artery and it takes a special touch to get that one. You don't want an amateur digging around that deep. But when they pull blood out, it's bright red, because it's that iron in the hemoglobin is attached to oxygen, and that changes the spectrum, the absorption spectrum for iron. When you pull it out of an artery, it might look slightly red, but it's really kind of a purplish color. Or a dull red, right? Because it's lost a lot of its oxygen. There's this other, and that's due to the element iron and the way it's attached in the heme molecule. But you can also get reds from this molecule. I studied this one when I was a master's student working on crawfish processing waste in Louisiana. And crawfish, they're like most crustaceans, crabs and lobsters, especially when you boil them, they turn red. And they turn red because of this molecule and some closely related molecules. What you'll notice is wherever it's zigzagged, wherever you change its direction, there's a carbon atom there. That's the way organic chemistry works. So there's a carbon at every one of those junctions where they go up and down, plus the ones that are labeled. And what you'll notice is it's an alternating single and double bond all the way across there. That leads to what's called conjugation. It spreads the energy out more evenly across the molecule and lowers its absorption spectrum into the red region. So it's red, just like hemoglobin is red, but for different reasons. Okay, so the official name of light is electromagnetic radiation. It's called electromagnetic because as light was being investigated in the 1600s up until present, what was recognized was that light had two components that could be identified. One is a magnetic component, and the other was an electrical component. And it's usually depicted as right angles to one another. So the waves of light is traveling this way, and we're going to show you a wave in a minute. It's traveling this way, and oscillations this way might be magnetic, but oscillations this way would be electrical. So it carries both of those characteristics with it. Now, if we want to describe light, and this is the way it was first described, as a wave, we have these three terms. The wavelength, right? The wavelength is represented by the small Greek letter lambda, that wavelength. And that just means the distance between two consecutive crests. a wave. So you can say wavelength about anything. I mean, if you see ripples on a pond, they have a wavelength, the distance between two crests. If we represent light as a sine curve, then the distance here to here is one wavelength, right? And of course, we measure it in meters because that's the standard, international standard measurement. But sometimes for convenience, of course, we use different units of measure. May use centimeters, may use nanometers. Right? Remember what a nanometer is? Nano means 10 to the minus ninth. So it's a really, really, really short distance. Anyway, this is the wavelength. We can also describe this wave in terms of its frequency, which is the Greek letter nu. Or sometimes I've seen some textbooks now, they're starting to use just an F because most people don't know what the Greek letter looks like. And you can get it confused with a V when you're printing it out in an article. So maybe they'll use F because I'm going to use nu because that's the way I learned it and it just feels natural. But the frequency, this is in meters. This is in cycles per second. Cycle is a dimensionless number. It has no dimensions. So in reality, what we're saying is reciprocal seconds is the unit of measure. And what that means is if we position your eye here and we count 1 second, we count how many waves pass your eyeball from this point to this point, not this one, the top. Count how many waves pass your eyeball in a second. That's frequency. So that's why we say cycles per second, because it takes into account what we're counting. And then the last unit that we're interested in is speed. And we give that a small c. Right, so this will be reciprocal seconds, this will be meters, and this will be meters per second. And this just means how fast does this point get to some other point? It'll go so many meters in a second. And in fact, in a vacuum, it's 2.9979 times 10 to the 8th meters per second. So it's pretty quick. That's in a vacuum, and it's pretty close to that even in air. I mean, it'll vary some, especially with the temperature of air. Right? Temperature will change the density of air, and that'll change its speed. So if you're out in the desert, right, and you see a mirage, you think it's a pool of water. No, it's the way the light bends when it goes through air of different densities. We'll talk more about that later, I think. Okay, and all three of these are related to one another with this formula. We can say the speed of light is equal to the wavelength times the frequency. And if we do, like I like to do, is dimensional analysis. Put the units in here. The wavelength is meters, right? The frequency is reciprocal seconds. So meters times 1/seconds is equal to meters per second. That just confirms that the formula is at least half right. It's got its dimensions right. So it's like any algebraic expression. If we know two of these, we can solve for the third one. Okay, this is just to give you a feel, like sort of introduce you to the intuition of light. You'll see at the top, we've got this span is 1 second from left to right. So over the span of 1 second, we would get, for a longer wavelength, we would get fewer cycles per second. So they're inversely related. And if you look at the formula, that's what we get. This is a constant. So if these are variables, then if one goes up, the other has to go down. Right? And we're going to look at another inverse proportionality today in the lab, Boyle's law, right? Where we have constant is equal to pressure times volume. So you got the same layout. Products equal to a constant are inversely proportional to one another. All right. So this is what the spectrum looks like, a representation of the spectrum. The first thing that pops out is, of course, the visible. And if we assume that the range of wavelengths in this representation are proportional, right? They're like they've scaled properly. Then we find that the visible is just a very narrow range of wavelengths in the whole spectrum. All right, so if we lay it out as the shortest wavelength is going to be the highest energy, which is gamma rays. And the longest wavelength, it can be 10 to the fourth meters, 10,000 meters long for one wave. Those are radio waves. And you can subdivide the radio waves into what we use for FM radio or AM radio or shortwave. And the shortwave likes that region in there, those wavelengths, because the Earth is surrounded by an ionized layer high up, upper atmosphere. And if you blast your shortwave signal out at the wavelength in that region, it'll bounce off of that ionized layer, and you can go around the curve of the Earth and talk to somebody on the other side of the planet. It'll probably go bounce off. It'll be a reasonably strong signal if it only bounces once, but it could bounce off the Earth and go back up and bounce and talk to somebody on the other side of the planet. Microwaves are a little shorter wavelength, right? Everybody's familiar with microwaves. A certain wavelength of microwaves is what we use to cook our food. Right? And the reason we do that is because that particular wavelength is preferentially absorbed by water molecules. Most foods have water in them. So we hit it with a microwave, the water molecules absorb that energy, and they get excited, and they transfer that energy to the rest of the food. That heats it up. Then a little shorter wavelength is infrared, right? And it's just a little longer than the red end, right? And the visible, everybody remember grade school, how to remember the colors? Right. Red, orange, yellow, green, blue. I never got the difference between these two, indigo and violet. I think they stuck that one in there just so it would flow better. But the red is on the long wavelength side. The blue is on the short wavelength side. So we have to flip it around for this particular slide. And then shorter wavelength than blue is ultraviolet. Well, shorter wavelength than violet is ultraviolet. And then we get into even shorter wavelengths for X-rays, right? And everybody knows how X-rays go. Trying to find broken bones and cavities in your teeth. The nice thing, though, is now most dentists don't use film anymore, right? They use the electronic detectors, and you can get away with much lower exposures to X-rays with the electronic detectors. So I could probably go, 10 X-rays in my teeth for the equivalent of one film X-ray that I had as a kid. And then the very shortest wavelengths are the gamma rays. Those guys, you have to produce those artificially on Earth. But nature produces them when, supernova explosion or two black holes crash into each other, those types of things. Or even when whole galaxies do something strange. We get these gamma ray bursts that come from deep space. They're very directional, right? They do spread a little bit, over the many light years that it takes for them to travel. But these gamma ray bursts carry massive amounts of energy. If we ever received a direct hit from a gamma ray burst, it would strip the atmosphere from the Earth. They're that powerful, even from billions of light years away. Fortunately, the probability of that ever happening is very, very slim. We know that they're out there because we're kind of off to the side, and we catch a little bit of the radiation so we can detect it. Yeah, they're there, and we can study them and see what caused them. But that's the spectrum. One other thing I'll point out is the units of measure, especially for the visible range, right? The visible range goes from the blue, 10 to the minus 7th meters, to about 7 times 10 to the minus 7th meters. But scientists don't like to use scientific notation unless we absolutely have to. That's too much trouble. So we change the units of measure. So we're going to convert this to nanometers. So if a nanometer is 10 to the minus 9th, why don't I store up some more information and put it over here? So 400 times 10 to the minus 9th meters, right? If I move it this direction, I'm making this one bigger, so that one's got to get smaller. So I make it 400 times 10 to the minus 9th. That will make this one 700 times 10 to the minus 9th. And now I can change this to nano. And that's 400 nanometers to 700 nanometers. Okay. In case you see nanometers, then you won't be freaked out by it. Then there's the issue of energy transfer. One of the laws of physics and chemistry, for that matter, is that energy is not created and it's not destroyed in any process, whether it's chemical process or a physical process or nuclear process. Energy is always conserved. So when we hook this pickle up to a high voltage direct current, that energy that's traveling between those two electrodes, and it will travel because the pickle is a conductor. It has vinegar in it, which is a reasonably good conductor. And some of that energy is converted into heat. And it's converted into heat. We don't see it glow at first, but we could feel it getting warm. And eventually it gets hot enough. Now some of the energy that's making it hot is converted into light. I mean, it's the same amount of energy that came from that battery, but now it's taking different forms. And one of those forms is light. And this brings me to the topic of black body radiation. I'm trying to remember who was studying this. I think it's in a slide, so I won't bother trying to rack my brain. What we mean by black body radiation is if the body, and especially this is true for extraterrestrials like planets and especially stars, if they're heated and they're not really undergoing some chemical reaction on their surface, if they're heated, then the higher the temperature, the bluer the light. Okay, so stars that are blue dwarfs or white dwarfs are very, very high temperature. And we can calibrate that temperature based upon the color of the light that we receive. If they're red giants, like Betelgeuse, I say it 2 more times, it's cooler than the blue stars and the white stars. And it's because of this theory that anything heated to a certain temperature will glow at a given color of the visible spectrum. Actually, it extends into the infrared and the ultraviolet. also. And that's one of the ways that we know we can set up a regime that identifies the color of stars with its temperature. And it helps us propose. We can't prove this because it's remote, but propose the changes of stars as they go through their life cycles. I think that's how they figured. They're telling us that the sun probably has between 4 and 5 billion years left in its life because of its mass and its color. Okay, 19th century. We have this genius mathematician, James Clerk Maxwell, who proposed a series of equations based upon the wave nature of light. And when he published these at about the beginning of the Civil War, only he was in Europe, so he didn't have to worry about that. He described the wave nature of this electromagnetic radiation in these equations. And we're not going to look at those equations because that's beyond the scope of this course. But it is interesting that they are very effective. They're very accurate in describing the nature of light in terms of those variables that we discussed earlier. They're still valid today as long as we're discussing light in terms of its wave nature. Now, we're going to add a component of that in a little bit. It's also interesting that other theories can play into these equations. They're that flexible. General relativity, where you're talking about big stuff, like Einstein's large bodies, or very, very small stuff, quantum mechanics. And we're gonna look at quantum mechanics. We may not get to it today. Might have to wait till Thursday. So this, because it was so good at predicting the nature of light and how it behaved, scientists started to think that even at the dawn of the 20th century, most of our work is done. Right? All we have to do now is refine our theories about the universe, and we can sleep easy at night and collect our paychecks. But they were wrong. And there it is, Max Planck. At the beginning of the 20th century, was working on black body radiation. And he came up with an equation that equated the energy of light to its frequency. Right? So energy, we normally write it this way, proportional to the frequency. So more energy, more frequency, higher frequency, shorter wavelength. Higher frequency means more energy. And then if we want to turn this into an equal sign, we need a proportionality constant. And that's Planck's constant. There's a value for that. And when you need it, it's in useful information. Because I don't even remember what it is. I can get close, but I won't be exact. And this came out of his black body research. He also proposed that this energy, because this energy was related to the frequency in such regular amounts, he proposed the concept of the quanta, or the packet. Quanta is like a Latin term for a suitcase or a packet. So he proposed this, and other scientists ran with the idea. Quantized energy, and this is called a photon. Right? All fans of Star Trek know the photon because we put it in a torpedo. So this was the first inkling that light wasn't just a wave. Now it's related because there's frequency, right? But this idea of quantizing energy for light into a photon introduced the idea that maybe light had a particulate nature as well as a wave nature. Like wave is continuous. I mean, it starts here and it just goes. But particle nature means it's in this packet and it can go from here to here. Like one of the cars in a freight train. But we can use this equation, and if we know what the frequency is, we can calculate the energy. But if we don't know what the frequency is, say we know what the wavelength is, then we can combine this equation with this equation. Right? We just solve it for that term right there, and that's C over lambda. Then we take this equivalent and stick it right in there. Now we have another equation that we can use. If we know the wavelength instead of the frequency. And there's Planck's constant. It's a very, very tiny number, and that really doesn't matter because the purpose of this Planck's constant, 34, is to satisfy the conditions of going from joules to reciprocal seconds. That's why the constant is joule seconds. Its units are joule seconds. Joule seconds then times reciprocal seconds will cancel the seconds and leave us with joules, and that's what we want. That's the only reason that this number is weird, is just so that it can make that transition between these two. That's its sole purpose. Now, there are other equations where Planck's constant reappears, but it's derived from this original approach. Okay, I got a video coming up. Let me see if yeah, it's 100%.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also—
What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
To summarize, the video introduced Einstein and the work that he did that won him the Nobel Prize in 1921, I think it was. So he did the work. Usually the Nobel Prize isn't awarded until about 10 years or more after the work is published, because they like to be sure that it's reliable and accepted by the scientific community before they start giving prizes. But Einstein won the Nobel for his mathematical treatment and description of the photoelectric effect. So now we have to describe, okay, what's the photoelectric effect? These are the observations that lead to that type of description. And this is headed toward the particle nature of light. Okay. No electrons are emitted by metal. Okay, now we have to be more specific. Say this is the surface of a metal. And you've got light coming in like this with its energy. Okay. And it's in the packet, right? It's photons. Well, the energy that is assigned to this light has to be a certain minimum amount, and it's dependent upon what metal you're talking about. Right? It would be different for different metals, the amount of energy required. And if it reaches that threshold energy, then you can release an electron. Now, that's the minimum amount of energy to take that electron from the outermost shell of the atom to a position we call infinity. It's actually released from the metal, but it doesn't have any energy of its own. I mean, it doesn't have any velocity, it doesn't have any momentum or kinetic energy of its own at that minimum energy. But if you exceed that amount of energy in your photon, then the extra that you use up some of it to release the electron, and the extra is used to accelerate that electron to a certain energy. Okay, that's going to be one of the points here. I'm getting ahead of myself. Below that frequency, which is energy, no electrons come off. Now, the concept, the idea, before this photoelectric effect was observed and described by Einstein, the idea was that all you needed to do was for any light, didn't matter what it was, white light, blue light, orange light, red light, all you needed was to make it more intense. And you would start to get electrons come loose. But it didn't work that way. So all the intensity does is increases the number of photons striking the surface at that given energy. Okay? And unless they were a sufficient energy, you get no electrons. Now, if these photons were exceeded that threshold energy, then instead of one electron coming loose, you get many electrons coming loose. Okay? So below this threshold energy, no electrons are emitted, no matter how intense the light is. And we multiply the number of electrons that leave the surface based upon the intensity of the light. And I mentioned this, the kinetic energy of the electrons is recovering the excess energy above the threshold that impinges on that surface. Okay. One of the conclusions of this is that the electromagnetic radiation must arrive at the surface in discrete packets. And each packet has enough energy to eject one electron. So one packet, one electron. And that there's a minimum amount of energy needed to excite an electron to a level that exceeds the atom's ability to hold it. Right? So you go from the atom in the atom's sphere of influence to infinity, which is released from the atom. The energy, now we have to conserve energy. So if the light is below the threshold in energy and it doesn't eject electrons, we have to do something with that energy. So if it's not reflected, if it's not a shiny surface, then it's absorbed by the metal and the metal heats up. right? Those are called thermal photons because they don't have enough energy to eject an electron. I already mentioned this one, so I'm not going to go over that. And this one also. That's just beating the dead horse. So what does the photoelectric effect tell us about the structure of the atom? There's an interaction of light and matter that happens with the electrons. Okay. I mean, that sounds simple, but when it was proposed, it was kind of revolutionary that light would interact with matter in this way. And the electrons were the ones receiving that energy. The absorption of this photon is tuned to the movement of an electron from one energy level to another. In other words, we're starting to see that not only was Rutherford right in his structure, these outermost electrons now can jump from here to infinity with a certain energy of light. And in fact, future observations that aren't related to the photoelectric effect, we can move electrons from one energy level to the other by absorbing a certain energy of light. That's what I was doing with my spectrophotometer, right? This was a ground state, stable atom in that flame. I was shining light through it, and it would absorb a characteristic wavelength of light because it would only move from one level to the next. It wouldn't move in between, right? The movement of electrons are quantized also. And that's the type of information that we get from studying the light that's either emitted or absorbed by atoms. All right. Now, the last item is if this electron is accelerated with an excess amount of energy, it's going to be kinetic energy, right? It's moving, which means by this formula, the electron has mass. It has to. Otherwise, it can't have kinetic energy. I'm sorry, light. The light can be equated to, no, the electron, I'm sorry. The light gives it the energy. The electron itself has mass. I'm getting ahead of myself. We can actually equate the energy that's contained in a photon of light with its equivalent mass. Or we can say, I have a certain mass. I also have an equivalent energy that's associated with that mass. So Einstein also taught us later that energy and mass are interchangeable. E equals mc squared. There's my favorite picture of Albert Einstein. It was when he was kind of elderly. You know how elderly people are. You get to an age where you don't care what people think of you. So he showed us his comic side. So in 1905, Einstein proposed the special theory of relativity. And this is the theory that he published that proved that, mathematically proved, that light has mass. Now we have to be kind of hedgy on this. He's talking about relativistic mass because the special theory of relativity, things they have to move near the speed of light in order to manifest this trait. Right? We don't have time to deal with that. I'm no expert either. But we can convert mass into energy, and this is the principal formula that nuclear scientists use when they're judging how much energy we can expect from nuclear fission or nuclear fusion. You take the original like U-235, and it splits into two smaller atoms. I can't remember what they are. I think one of them is thorium. Anyway, you take the mass of this one and the combined mass of these two, and this one is less than that one. These two less than that, right? Well, you have some neutrons out here too. They're speeding up. But you account for all the mass that you can collect on this side, compare it to this mass, and you find that it's less. The difference in mass is converted into energy. That's why the atomic bomb is so powerful, or nuclear energy is so powerful, because you can take just several pounds of uranium-235 in the proper mix with 238, put it in your nuclear reactor, and it'll run for 10 or 15 years without refueling. Or put it in a nuclear submarine, and they can go for 10 years without refueling. Because C squared, right, that big number, 10 to the 8th squared times the mass equals your energy in joules. So that's why the energy is huge for just a little bit of mass change. Einstein proposed this theory, and this is not the one he got Nobel Prize for, but it was just as revolutionary. And Arthur Compton, it's a funny thing with physics, it's divided into two camps, right? You have theoretical physicists who work with math, and just thought problems. That's all they do. Einstein was one of them. What was the can't remember his name. The physicist that had Lou Gehrig's disease, and he's dead now. Hawking, thank you. Yeah, Hawking. That's all they do. They just think all day long. And then there are experimental physicists who do their own work, and sometimes they collaborate or they take theoretical and they try to prove it. So Compton in 22 experimentally confirmed this E equals mc squared. Now that brings us to the idea, and then there was, in the beginning of the 20th century, there was a raging battle in the sciences going on about the nature of light. There were those who clung to the idea that light was a wave, couldn't be anything else. And then there were these new scientists who were saying, well, no, look at these photoelectric effect, right? Light's behaving like a particle, you know? So what they came up with was both are correct. Light has both natures at the same time, both particle and wave. Now, when we investigate it, depending on how we look at it, we can look at the particle nature or the wave nature. Okay? The evidence for the wave nature is manifested in these different phenomena. This first one we talk about is called diffraction. Diffraction of a wave is the way the wave behaves when it strikes an edge or a slit or a pinhole. When it does that, in this case, it strikes this pinhole, and the wave front strikes there, and the pinhole serves as a point source for a new wave. It may have the same wavelength, right? But it's starting from that point and it's radiating out. And now if we have two pinholes, like if we had this, and that same wave was here, had struck here, and then it was going out like this, what you get is interference. So these lines are like the peaks, right? And where two peaks cross, you get constructive interference. You get a higher intensity. And where you get a peak and a trough meet, you get destructive interference. and you either get canceling out or you might get a dip. And you can see that on your detector over here. The strongest will be right here, right? There's nothing coming through here, so it can't travel straight. But the strongest signal is right here, halfway between them. And then you get the blank area, and then you get something that's a little lighter, a little lighter, a little lighter, a little lighter as you go out. Get this called interference pattern. Okay. So this is due to diffraction. This principle is used for if you have building a spectrometer where you need to split the light that strikes it into a wavelength pattern. Used to use prisms because that's all we knew. But the thing about a prism was, as the light passes through the prism, some of it's absorbed by the prism and it decreases the intensity on the other side. And you don't want that. You want a strong signal when you're trying to detect an element of some kind. So the nice thing about this phenomenon of diffraction that was built into mirrors, they'd have the glass ground to a certain shape so it would focus. And then they would etch very fine lines. And what happens is when the light strikes those lines, it would generate a diffraction pattern. And they would come off and they would interfere with one another. So depending on which way you twisted that mirror, you would sweep through the different wavelengths that were contained in the original signal. I used to operate an instrument that was based on that. So diffraction. Refraction is what the light does when it travels and it breaks between two media of different optical densities. So in other words, if this is air and this is water, right? And you got a fish over here. Then if you're looking at it, if you're looking, say your eyeballs up here somewhere, then the light that comes out of there is going to be bent toward the more dense medium. So the light would come out from the fish, and if it meets your eye, it would have come from here. So you think it's over here because that's a straight line, but it's really over here. Another way to look at it is if you have the medium here, say we have air and glass, okay? And you have the wave coming in like this, and it meets the glass, it slows down, right? So this part of the wave has to slow down, and this part slows down, which eventually changes its direction from this way to that way. That's not much, but it does. It bends light as it transitions between two different media. That's refraction. And that's what we base our eyeglasses on, right? It's what we base originally our telescopes, right? Telescopes, the biggest lens ever built was 40 inches. I think it's 40 inches. Lick Observatory. It couldn't make it any bigger because in certain positions when you move your telescope, the lens would sag and change its focal point. So they couldn't make it any bigger. So they went to mirrors. Right? And the biggest one on Earth until several years later, they're starting to make bigger ones. But the biggest single mirror was the one on the Palomar Observatory. Had a 200-inch mirror. Now they're making big ones. In fact, we sent one out to the Lagrange point beyond the moon that was the James Webb telescope. And it's like, oh, let's see, I think the mirror is about that wide. It is huge. Actually, it's even bigger than that. But bigger mirrors in space allow us to see further. We can pick up. In fact, in the James Webb Telescope picks up light that's infrared. So the nice thing about that is infrared light can pass unhindered through dust clouds, right? And a lot of the stuff we look at in the universe is obscured by space dust. Now, it may be very tenuous on a local level, but when you're looking through light years of dust, it can be a problem for your observations. Okay. And the primary indicator for particle nature is photoelectric effect. All right, how we doing? 1:30? Okay, got 15 minutes. Let's talk about the type of light that can be received either locally or from space. If we have the spectrum, if we have a continuous spectrum, that simply means that we get all wavelengths possible. Right? We put the prism in there and we shine light through it, spreads out into the different colors, but every color in the rainbow is represented in that white light. It essentially contains all the wavelengths of visible light. Whereas a line spectrum only contains specific wavelengths, and they show up as lines. Okay. One example is the hydrogen emission spectrum. It's the easiest to interpret because it's only got one proton, most of them, and one electron. They're really simple. Right? And that's one of my favorite bands.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Is he done? Yeah, I think he's done. Okay, so what they're trying to show us is that this line spectrum indicates that we've got, let's see, 486. These visible lines that are coming from the hydrogen atom. And then the last one is 411. Are traceable to movement of electrons in this space around the atom. And the hydrogen spectrum is very, very simple because it only has one electron and one proton. There's no interference between multiple electrons, which tends to modify the absorption lines. So this one is very simple. What you'll notice is that the farther the electron drops, the shorter the wavelength, which means higher energy. Okay, so the energy increases in this direction. Based upon the jump. And we don't see any wavelengths in between here. So that tells us, this is giving us information about the atom. The electrons jump only from these energy levels, right? And notice we're not jumping to the first level. This is the visible range. Right? We can see these colors. If we jump from any one of these to the one, we're going to be into the ultraviolet region, and that's a different spectrum. You need instrumentation to detect those. Now we have evidence that the movement of electrons inside the atom is a quantum feature. It moves in only packets, in specific quanta, from one energy level to the next. Why is it significant that the color emitted from hydrogen is not white? And how does the emission spectrum support the idea of quantized energy levels? Well, first of all, if the levels were not quantized, if we would see white light, that means the electrons were free to move from any distance, any position to any distance. That would give you every color in the rainbow. And that would be a problem. We observe these colors, and that means that only certain movements are allowed. And that's leading us to understanding the structure of the atom as electrons that occupy these energy levels. So when we start to take atoms and put them together for chemical reactions, the interaction is between these regions of the various atoms, the outermost regions. That's where we get the chemical activity. Oh, and speaking in terms of probability, the probability of finding an electron in here is 0. Those are called nodes. Okay. So this observation led Niels Bohr, who was a relatively famous chemist, physicist, about the same time as Einstein. He proposed the Bohr model of the atom. And this is a representation of the Bohr model. He was thinking in terms of planetary model, where the sun would be the nucleus and the planets would orbit in these positions. Okay? So if one of these electrons in this position was considered like a planet, then we should be able to figure out what its energy change would be from one level to the next. Because physicists had been working on that for quite some time. So the Bohr model also had what's called a ground state. Now, the ground state is where the electron is at its lowest possible energy at a given temperature and pressure. So at room temperature and pressure, ground state would put the electron right here. I need to throw those out. It's the end of their life. And he gave these numbers are Bohr energy level numbers. N equals 1, N equals 2, 3, 4, 5, and 6. They get larger as you move away from the atom. So the lower energy values are for N1, then a little higher energy for N2, so forth. All right, we already talked about this. And this. I want to get to actual discussion of the Bohr energy calculations. So here's the equation that Bohr came up with, and notice that it has a proportionality constant. We call that. Sometimes we call it fudge factor, where we can calculate the energy of any one of these electrons in a different energy level. If we say this constant minus 2.178 times 10 to the minus 18th, and then multiply that times this ratio, right? And Z is what you think it is. It is the atomic number. For hydrogen, it'll be 1. And N will be one of these energy levels. So we plug those energy levels in here, we plug 1 in here, and we come up with an energy value in joules. So if we want to know the difference in energy, which allows us to calculate this value, right? Each one will have a different energy. We need to know what's the energy at this level and what's the energy at that level. Then if we take this higher energy, subtract this lower energy from it, gives us a number, then that energy in joules can be equated to wavelength with Planck's equation. Or we can combine the two. We can say, okay, let's just say one is, say, in final and in initial to locate the positions of the electron. If we do that and combine the two, then we get this equation, which we're going to reduce. Okay, final minus initial. And we just factor out that constant. And now inside the parentheses, we have the Z, of course, is still 1 and 1. And the N then is the only variable that we change in there. So the final initial N2 would be, say, we make it 6. And then the N initial would be 2. So it would be 1 over 6 minus 1 over 2 times that negative number gives you a positive energy value. And that energy value you can plug in here, and that's a constant. You can solve for the frequency. Or with the other equation, you can solve for the wavelength. And what we find is that when we do this calculation, it agrees very well with these values here. Okay. So if we go from level 5 to level 2, there's our equation. We plug in the 2 for the final, 5 for the initial, and we get an energy of minus 4.57. Let's see. That's right, minus the 1/5 is smaller, or 1/25 is smaller than 1/4. So that the energy change is negative. So what does that mean? Well, remember when we talked about systems, the way we treat systems thermally, right? Everything is referenced to the system. So if the value is negative, energy is leaving the system. So with this negative energy value, we're saying that energy is leaving the atom. That's how I make sense of it. But when you're calculating the wavelength, you don't need the negative. You just plug in the number and do the calculation. And it's going to be the same energy with a different sign, depending on which way you go. Right? So if we take the 434 nanometers and convert it to meters, of course, and plug it into our equation for energy, then we come up with an energy of 4.5 times 10 to the minus 19th versus 4.5 times 10 to the minus 19th. So it just confirms the Bohr's model works at this level. And whenever you hear model, think theory. Theories have models, laws don't. So, one thing that goes wrong with Bohr's model is that it doesn't work for anything but hydrogen or hydrogen-like. So if I had, let's say, lithium, right? Lithium has 3 protons, right? So it has 3 electrons. So if we want it to be hydrogen-like, it has to have only 1 electron. And it's out here, only 1 electron. So that means if we take away 1 proton, take away 1 electron, that makes 1 positive. Take away 2 electrons, that makes 2 positive, and now we only have 1 electron left. Right? We started out with 3. So we take away 2 of them. So a lithium 2 plus would work for this formula. We just change this value to 3. Okay? It does work in that way. We can't have multiple electrons for this model to work because electrons have the same charge and they interfere with one another. And that really screws things up. But Bohr he started the ball rolling. We're gonna get to a better model eventually. So quantized energy fits the Bohr model fairly well. Electrons become more tightly bound as they get closer to the proton, right? So it takes more energy to remove them when they're down here. When it takes more energy to move them up the levels than it does from here. It only works for hydrogen or hydrogen-like molecules. The other thing that didn't sit too well with physicists from the very beginning was its planetary model, saying that electrons move in circular orbits. We know from physics that if they move in circular orbits, they're bleeding energy. So eventually those electrons will spiral into the nucleus, but they don't do that, right? So we got to solve that problem. And I'm not going to spend time on this one. It just illustrates the fact that the bigger the jump, the shorter the wavelength and higher the energy. And I think, yeah, we're going to pick it up right here on Thursday.